Layton with a GH. All right, but that's enough before someone asks me and I can't.
What's my social security number?
All right, hello. Today's tute is not so long, which is good. Still get you out of here early. But before we do, I have uploaded the solutions to tute 5, and I've uploaded tute 6, and I've also uploaded the solutions to tute 6. I want to make sure that you have all of the vector calculus material before you go and study. So even though you won't do the material in the tute until the first week back, I want you to have that available to you to help your study over the break. So make sure you know that that is there. Good. All right, so Mathematica, important visualization tool, particularly for vector fields, important ideas in vector calculus. And what we did this week is we looked at taking these ideas that I gave you last week in R2 and said, well, what are the natural R3 continuations? And to think about fields in R3, it is very helpful to be able to imagine what fields in R3 look like. So that's what this is about. So we start off by looking at this vector field here, and we can say a few things about this vector field before we hit enter. So the top is yz, and the bottom is x squared plus y squared plus z squared, which sort of suggests that if I pick a direction and go in it, the field is going to decay. But if I move in, say, y and z at the same rate, then maybe it won't decay, because I'll get y times z, which is about as big as y squared or z squared, so it might tend to a constant instead. There's a lot of things you can say about these fields without necessarily actually calculating them, and being able to look at a field like this and pick out qualitative properties of it is a really helpful trick to be able to pull. So before we look at it in 3D, let's look at the equivalent field in 2D, which using streamplot looked a bit like this. This is a very neat kind of field. When you start to think about vector fields in the context of differential equations, what you will call this is a bifurcation point. But it's, maybe it's a bit saddly, you could think of it. And this is quite nice. But now let's look at this 3D vector field. Now, Mathematica is a little more limited into how it can plot in 3D. It can only really do vector plots. It can't do stream plots, but that's fine. I mean, you can poke around and sort of start to see what's going on. Visualization is a bit harder in 3D because of the extra dimension. This should come as no shock. But you can start to see, all right, maybe if I sort of follow around here, you can see something going on like that. But I don't know, I'm a little bit lost. And probably you are too, although you might be better than me. However, Mathematica has a really nice function called slice vector plot. So here what I'm saying is I only want to know the vector field on the curve defined by x squared minus y squared equals z. Okay, so now I'm looking at a 2D cut, and the field is becoming a little more obvious because it's only the bits that I'm interested in that I can see. If I want to integrate along this surface, I don't really care about what the field is doing everywhere else. I care very much about what the field is doing on this Pringle here. So you can see there are some places like here where it seems to be almost parallel to the field. There are some places like here where it seems to be almost normal to the slice. So if I integrate the field there, then I'm probably going to, have to project that onto the direction, and that's a bit harder. But remember, when we talked about surface integrals, we were mostly interested in the flux of a field through a surface. We'll talk about tangents in a bit, but it's a little bit tougher here. So we're interested in the flux of the field through the surface. So it makes sense, instead of plotting the vectors on the surface, which is nice and helpful to visualize, maybe all I need to know for what I'm trying to integrate is the normal vectors. So here what we have is the vectors are shown. So the vectors are still there, but what we've plotted on top is just the normal vector. This is a bit hard to see. So we're going to plot that, but we're actually going to get rid of vector slice entirely. Hopefully this works. Wrong program. Comment this out. Fingers crossed it works. And now I should just get, no, I don't know why that didn't work. Let's just keep going where it does it anyway. So now, here is the original, but we're trying to put everything together so we can finally get something that has everything going on. So you've got the actual field, and in a much smaller way, the normal vectors. Why that is relevant, I don't know. This is the important thing, which shows that, okay, so this wasn't obvious from the field we saw before. From the field we saw before, maybe we could have said, well, actually, there's not much normal stuff going on here, and there was a lot of normal stuff going on here. But I can see straight away I was a little bit wrong about what was going up on the top. There's actually a decent chunk of normal contribution there. So you can start to visualize the field that you're looking at, to think of this as an object that exists on that slice. Now, we only really care about it on that slice because we're interested in knowing specifically what is happening on that surface, and nowhere else really. And of course, as we know, because goodness knows I wouldn't stop harping on about it, if you know what's going on a surface, if it's closed, you probably can infer what's going on inside of it as well. Okay, so we have the vectors of the surface. You want to get the normal component of the vectors, and in this case, we did the calculation. Minus fx minus fy, 1. Now, Mathematica doesn't have that built in, but you're all very smart advanced second years who remember how to calculate that. So the thing you want to integrate is this. So this is the field projected onto the normal direction. Looking pretty good. Now we're at the point where we actually need to start telling Mathematica a bit more about what to do. We've kind of shot past all of the inbuilt functions, and now what we're doing is we're evaluating this integral over our region. So we want to integrate this thing xy, and we've got a nice iterated integral, which you're all very good at. X goes from minus the square root of 1 minus x squared to the square root of 1 minus x squared, which is, of course, a circle, and y from minus 1 to 1. So what we're tracing out here is precisely the unit circle. Probably you could do this in polar coordinates. I don't think there's any reason to, though, when we have a computer in front of us. And it tells us that this is 0. This was a surprise to the person who wrote this worksheet when they computed it. I don't think it's a surprise. The divergence isn't 0, so it isn't the curl of a vector field. This is not like Stokes' theorem 0 situation. This is not conservative. This is more of a mathematical coincidence. That can happen, right? Sometimes integrals are 0 for no reason other than the amount of stuff is cancelled out by the amount of other stuff. Okay, but we can compute. We can compute this, so we look at a plot of what we're integrating, and you can start to see why we might have gotten 0. Okay, so the integral gave us a value of 0, and we can see 0 is in about the middle. So there's some stuff above 0, there's some stuff below 0, there's a catastrophic failure at the origin, which is actually fine. Because it's what we call a removable singularity, it doesn't blow up off to infinity, then the definition of the Riemann integral is robust to a single point being removed, because you can still come up with all the partitions you need to. It's still bounded on that interval, except at the point that you care about. Okay, but what if we want to confirm our intuition and say, well, yeah, okay, there's about as much of this above 0 as there is below 0. It's got this nice fourfold symmetry-ish. I don't know if it's precisely. It looks precisely. Yeah, it is. Where there's about as much stuff above the origin as there is below the origin. Whenever you have an integral that is 0, it means there is about as much stuff above the origin as there is below the origin. I'm stressing this. It's possible if you want to answer one of the trickier questions from this week's Canvas quiz, that might be an important thing to remember. Who forgot until this instant that there was a Canvas quiz this week? Good, great. Everyone forgets the quiz the week after an assessment. There is a Canvas quiz this week. It was in the announcements. Thank you. Yes, it was. Read my announcements, guys. Okay, so if we actually did, so here we do some calculations and show, well, actually, if we explicitly calculate out this, but on an unscaled version, so y, z, x, z, x, y. And this is a sensible thing to do because the scaling was completely symmetric. So you would expect any cancellation of the scaled field would be reflected in the actual field. And here it's a lot more obvious that we should expect cancellation because you'll get y being positive, y being negative, z being positive, z being negative, x being positive, x being negative, and you'll get one of each. So, you know, you've got a quadrant where x and z is both positive, a quadrant where x and z are both negative, so those are both positive overall. But you also get a quadrant where x is positive and z is negative, and a quadrant where x is negative and z is positive, which should cancel those out. So when we write it this way, the cancellation is a lot more obvious. And now here, what we discover is that you can write this as curl of a vector field. So we can come up with some g such that the curl of f is g. And this is something I talked about today when I mentioned the Helmholtz decomposition, is I mentioned the scalar potential, which we all know and are completely familiar with and are going to knock out of the park on a midterm test. But I also said there's another kind of potential which talks about the divergent part, except that's a vector potential. And in this case, what we've just constructed here, and how you construct this is an exercise for the tutorial, is that the curl of this gives us our original vector field. So in fact, this is a divergence-free field. It has a vector potential, and we constructed it. And we can use Stokes' theorem, and of course, because the divergence is 0, Stokes' theorem is very easy. So we do a few calculations, not very interesting, but here what we're doing is parameterizing our path in x, y, z. So we're going cos t, sin t, cos 2t. Gross. Sorry, yeah. Then we calculate our vector potential on that curve. So where there's an x, we replaced it with cos t. Where there's a y, we replaced it with sin t, and where there's a z, we replaced it with cos 2t. There are ways to do this more directly in Mathematica, but at that point, the juice is not really worth the squeeze. You know what x and y and z are, just put them in yourself. We'll do that. So you do the calculation, and you say, well, God, I hope this integral is going to be 0. You calculate the thing you're going to be integrating over, and it's sine 2t plus sine 6t with some constants. And we're integrating essentially 0 to 2 pi. So you're going to have as much sine above as you are below. You're going to have as much sine 6t above as you are below. And now, integrating a periodic function along its period, if its mean is 0, is going to be 0. And sure enough, the integral is 0. So this makes sense. If I gave you a vector potential and said, hey, well, if you take the cross product of this, you get the divergence, then you should feel very comfortable saying, well, I know what to do with divergence because I have all of these fundamental vector calculus identities. All this worksheet is doing is stepping you through the implementation of those vector calculus identities. Don't overthink what this worksheet is telling you. It's the least sophisticated one we've done so far. Vector plot, and this is over the monkey saddle, which is to say the triple saddle. So let's take a look at what's going on here. There is no nice way to present this on this screen. What I want is a better aspect ratio, but I don't think that's going to happen. So there is a lot going on near the middle. Here they're positive, here they're negative. There's a bit of a flip here, but we expected that from the structure of our field because we saw what our field looked like at the beginning. It had this crossover. Here, the vectors are pushing through. I can't really gauge how much normal. I mean, these are pretty normal. But these, I guess, some part of it is normal, some part of it is not. It would be much nicer if we could plot the normal component to the surface. Which isn't really what we're going to do. We're just going to calculate the normal component of the vector field relative to the surface. Okay. So this is my vector field, my x, my y, and my z, because I'm on the saddle, is x squared minus y squared. And here is the derivative of my surface, which is easy enough to calculate, which gives us the quantity we need to integrate over the unit disk. Here is how I do it in polar coordinates. Why not? Turns out it's a bit easier. So here they've just said, all right, x is r cos theta, y is r sine theta. We know that's a polar coordinate transformation. It makes sense to do this in polar. We're integrating over a unit disk. Why would you use any other coordinate system? We integrate, and we get 0. Again, this is another one where if we had sat back and looked at our function before doing anything, we probably could have short-circuited this procedure and identified that it was 0. Here's the thing that we're integrating over a disk, and here is the 0 axis. And you can see, look, it's not obvious from this structure that what we have is going to integrate to 0. And in fact, it's only from looking at that and realizing that the thing that makes it 0 is the fact that it is odd around the y-axis that gives you the symmetry you need for the total integral to be 0. And you can see, you know, this bit above is cancelled out by this bit below. Obviously, in an exam, you can't pull up Mathematica and look at the thing. In an exam, you just kind of have to trust me that I have set you something reasonable. But when you encounter an integral in the wild, all right, there are a lot of integrals in life which are so close to 0 but aren't 0, and these are deeply infuriating. So if you can come up with arguments as to why they must be 0, that can really speed things up. These are computational help. Everything we do in Mathematica is to reinforce the theory, but also to understand how we can not have to do the computations ourselves. Because mostly we don't do the computations ourselves, right? But of course, here we integrate it along a disk. We have a theorem about this. Maybe instead of integrating along a disk or along our monkey saddle, it makes more sense to integrate along the boundary of the region. Use a bit of the old Stokes theorem. So Stokes theorem says we need to parameterize our boundary. And this is kind of the buried complexity that we don't often mention when we teach you Stokes theorem, is that if the boundary is nasty, you're not actually getting a great deal of extra benefit out of doing it this way. You know, we did the circle because circles are nice and circles are easy, and I only have 3 hours to teach you. But here the boundary is cos t sine t, cos t cubed minus 3 cos t sine squared t. And that gives us the value of x as we go around this boundary. So we're parameterizing our curve in 3D, and then we just integrate along it in the obvious way. So we evaluate our g at x, at y, at z, and we take the dot product with the derivative of our curve. And I assume this equals 0. Well, something we're going to integrate is going to be equal to 0. I had a brief moment of panic there before realizing we hadn't actually done the integral. And look, maybe it's not obvious that that thing is going to integrate to 0, but it's pretty periodic, and we are integrating over 0 to 2 pi. So hopefully, maybe, integrating this thing from 0 to 2 pi is going to be 0. So here's the integral, indefinite, minus 1/8 cos 2t to the 4. I couldn't have done that. You are all better at integrating things in one variable than I am. I suspect you all would have nailed that. But if I integrate it from 0 to 2 pi, it comes out to be 0, as we would expect. Let's take a plot and see if this can help us explain what we just saw. Yeah, so if I look around the edge, you can see it's not totally obvious that there's as much up as there is down, because of course there's 3 ups. There's this up, and there's this big up. There's this down, and this big down. But take it all together, and you can see there's about as much above as there is below. Reckon I can put 0 in there as well so we can see this? Don't break, don't break, don't break. Yes. Oh, it's the same thing as before. Oh, well, that's disappointing. Let's integrate over a sphere. Okay, so here is our f3, our field, the function that we want to calculate. And instead of working out the curl myself, because I'm very lazy, I used the function curl. That's good. Do that. I use the function curl. And now I'm going to plot it on the hemisphere. Now this is interesting. I want you to look at this picture, and I want you to tell your friends something about it that jumps out at you. And remember, we are like looking at a picture and drawing qualitative conclusions. So, is there anything in there? Okay, all right. I'm hearing some interesting ideas, which are generally pretty good. Tell me something. Someone put up your hand. Tell me something about this picture. Yep. Looks kind of like the curl through the z-axis should be 0. Yeah, I respect that. Is that true? Yeah, I mean, you can see it's sort of diverging away, so it looks like the curl might have 0 component. Yeah. I think that is a distinct possibility. Anyone else? Got this hemisphere here. What about the field and the hemisphere? Yeah. It is, absolutely it is. Not what I was going for, but absolutely true and a very sensible thing to look for. If I was to say how much of that curl looks like it's acting normal to the hemisphere, looks like maybe none of it. It looks almost like that curl is entirely acting in the tangent space. And that's probably going to be true, but we should figure it out for ourselves. So we want to know about the normal component of the vector field, because if the normal component of the vector field is 0 of the curl, then everything is going to be living in the tangent space. We know that our normal direction is going to be minus zx minus zy1, because you all listened to me in week 1, because you are the dedicated ones who come to class. So now we just need to compute the dot product. But you'll notice that what we've done here is we have restricted it to the upper half hemisphere. So square root of 1 minus x squared minus y squared. What if I wanted to do this question for the whole sphere? Is there something I'd have to be a bit careful about? Harry? In versus out normals. That's right. If I let this happen, then I have to be very careful when I get to the lower half of the sphere. My normal is still pointing up, which means it becomes inward rather than outward. In class, we got away with this by converting into spherical coordinates. In this tute, we're getting away with this by only thinking about the upper half hemisphere, although we will relax this later in a neat way. Okay, so we want to actually do the calculation, which means we actually have to put together the integral. So here we project the curl in a direction. Right, so there's a bunch in this line, because we've got our curl evaluated on the hemisphere, and we are taking the dot product with the gradient. Remember, the gradient is perpendicular to level curves. So we are looking at the amount of the curl in the normal direction, and that is 0. I could never have told you this from the formula, but we had a hunch that this was the case from looking at the picture. Pictures are really good for hunches. And of course, you might go, well, I do things in full generality. You're looking at one picture. Oftentimes, looking at easily calculatable cases gives us an understanding of what we might find in these more general cases that we can then go through and prove and identify. It is not cheating to look at special cases and hypothesize what might be true, as long as you then go and prove the thing that is true, because you're still a mathematician. So use special cases to develop intuition, to start to hypothesize as to what things. My old PhD advisor said one thing is chance, but 2 things means there's something going on that you can find, right? Like, We could do one PDE and we found a bunch of behavior. We did a second PDE, we found similar behavior. We concluded that this behavior is actually generic to a whole class of PDEs. We started with 2 examples and we broadened out. Mathematica helps you very quickly look at examples and start to get important behavior. Okay, so what we're going to do here is verify Stokes' theorem. So the boundary is nice and simple. The boundary is at 0. The boundary is the unit circle. So doing a whole surface integral along here, quite complicated. Doing a nice integral around the unit circle, very, very easy. So what we're doing here is we are evaluating the curl at cos t sine t 0. And then we integrate along in the usual way. So we're integrating the curl around the unit circle. It gives us sine 2t. And we know when we integrate that from t equals 0 to 2 pi, there is much sine above the origin as there is below. This will be 0. I know this seems like a banal point, but in about week 10, we're going to start building PDE solutions out of Fourier series, which are constructed out of sines and coses. And all of these little throwaway comments I'm making about sine and cosine are going to come back with a vengeance. Okay, so the line integral will be 0, but what happens if we change the region we're integrating over but keep the boundary the same? Maybe, like in class, the smart move is not to integrate the curl over the hemisphere surface, and not to integrate around the boundary either, but to integrate along a different surface that has the same boundary. In this case, the circle on xy. So in this case, instead of having quite a complicated normal vector that's pointing out in the radial direction, we're going to have quite a simple normal vector. It points up. So what we are instead going to do, how far did I go? Here, good. We're going to evaluate the curl on z equals 0. And this becomes much simpler. And needless to say, of course, the curl at z equals 0 is not pointing up. It's, the curl has 0 vertical component. And if we plot this, we can see it. So this thing has 0 vertical component. The curl is just swirling around on the surface itself, just like it was doing for the hemisphere. So this is an example where it is very easy to see again that the flux of the curl through this surface is 0, because the flux of the curl is all of the flux that's going in the vertical direction, of which there is none. So you might say, I bet that happens on every surface. I bet you every surface I make that has this at the boundary, if I calculate out the curl, I will find that it is always living in the tangent space of the surface. But that's not the case at all. Because you might have some parts that are just cancelled out by positive and negative parts. And that's what we'll do in the final sort of piece. But here, hopefully you can see that the dot product of the curl normal to the with the surface normal is 0. The curl is acting entirely in the tangent space. I appreciate you're probably not laughing at me, but it is very disconcerting. It means that I have to quietly check my fly every time. Okay, so in this case, there is no curl flux through the horizontal surface. So it's 0. And in fact, any surface you chose would be 0. And some it's not super obvious that they would. So if I take this thing. All right, bit gross. This is a Pringle chip. You know, the boundary is not the unit circle, but you can come up with a graph that projects down onto the unit circle. The normal component of the curl, which we've calculated a bunch of times, so the curl acting in the normal direction is this. And it's not super obvious to me that that's not going to be 0, but we have Stokes' theorem. So instead of integrating that thing over a 2D region, which I don't know if that's going to choke my computer, but I suspect that it would, and I'm not going to try. What we can do is instead just integrate around the edge. One-dimensional integration is easier than two-dimensional integration. If any of you become numerical analysts, A huge amount of numerical analysis is writing problems such that they can be solved by integrals and then doing integrals around the boundary. Green's theorem, Stokes' theorem, these are tools you use every day to construct algorithms for simulation. Okay, so we've already parameterized the boundary of this in an earlier question. X is cos of t, y is sine of t, so it's moving around in a circle, and z is sine of 2t, so it's going up and down. Okay, the integrand is our field evaluated at x, y, z. Dot product in the direction of the curve is this thing. And now we can calculate the integral, and it's not so bad. It goes to 0. It doesn't go to 0 to infinity, so it's 4 minus 3 root 2 pi, which is this thing. So this one was not going to be 0 because obviously the field is a lot more complicated and the domain is a lot more complicated. If you integrate this numerically over that region, you will get the same number. But it will be hard. Okay. So the net flux of the curl is negative, and if you look at the flux of the curl over the domain, again, you probably could have picked that. You could have done a sanity check, because you can see there's more stuff below the axis than there is above. Integration is often as simple as asking, is there more stuff below than above? Which tells us that the sign is negative, and we've probably done something sensible, more or less. Okay, there are some more calculations here, but the last one I just don't think adds anything. It's just more involved ones, so I'm going to leave that one for you to do yourself. I don't think you need to see me evaluate a bunch more integrals here. I mean, you can if you want. Work out the curl, look at the pretty picture. Oh, no, this is a nice one, actually. There is just a point I want to make about this, which is you'll notice that, okay, it's a hemisphere, slightly distorted because of the aspect ratio, but it's not quite a hemisphere because it doesn't stop at z equals 0. It continues further, which means you might say, aha, I know what's going to go wrong here. If you use Cartesian coordinates, then if you use the obvious way of specifying the normal vector, it's going to flip from being the outwards normal to the inwards normal. And you want to be a bit careful, and you can see that here, right? So the field is just going vertically. But here, below, this is going to be in the direction of the inward normal. And here, this is acting in the direction of the outward normal. But it turns out it won't matter in this problem, and I'll just quickly show you why. So the curl is pointing vertically. So we really only care about what's happening in the z direction. Whereas our surface is this thing here. Strictly speaking, if z is less than 0, we should change our gradient to be z plus 2 times this square root. But we're going to take the z, it only affects these first two terms. But our curl is only acting on the third term, where the derivative is 1, no matter whether you were above or below. So strictly speaking, you should have changed it if you were being careful, but it is just worth pointing out that in this particular case, nothing changes, because the curl dotted with the gradient only sees the final term of the gradient. It is a very minor point. You can't possibly care that much about it, but if we do the integral and we look at the picture, then it should at least be nice. You can see here what we've done is we've plotted the outward normal everywhere correctly, and we've also identified the boundary. And of course, using Stokes' theorem, we know that the integral of the curl along that surface is going to be just the same as the integral along that boundary. Boundary should be oriented counterclockwise, of course, because in the statement of Stokes' theorem, it specifies that it's positively oriented, and you do the integral, and you get 3 pi on 4, which is exactly the value we got for a completely different surface. Okay, and the final example is the volume and surface area of a torus. We're not doing that. You can calculate it using volume integrals and surface integrals. Go through if you want. They have values. Which is to say, we've sort of now come to the end of the mathematical worksheet part of vector calculus, and like, I know not everyone enjoys the gross computation side of this. No one enjoys sitting down and shuffling numbers around. The point of Mathematica is to make it easy. I've been looking through the assignments. I'm not marking them, but I do like to look through to get a feeling of what people are doing. And one thing that jumped out at me was in question 2, the first multiple integration one, where I said, hey, look, get it down to a one-dimensional integral and then use Mathematica or some equivalent program to do the single variable integral. And to your credit, almost everybody did it using a computer program. But a disconcerting number of you used a large language model to evaluate an integral. And that is like using the dictionary to go, what is 3 times 5? Fiddling around until you find the definition of 15 as being 3 times 5. Like, yes, it gave you the right answer this time, but it's not the right way to do it. Use the program that is built for the purpose you want to use it for. I'm not saying that large language models can't correctly evaluate a one-dimensional integral. I think a grade 9 student could have correctly evaluated that one-dimensional integral. But I am saying it's exactly the wrong tool for the job. And the fact that it works doesn't mean it's the right way to approach this. Because if you move on to more complicated things, a large language model could not do some of these calculations. But Mathematica can. Because Mathematica is built to do this job, and ChatGPT is built to probabilistically string words together. Words are not the language we want to work in, so pick the thing that works best in the language we want to work in. Large language models have not obviated the need for mathematical computation, and you should get good at mathematical computation if you want to do mathematics. Or don't, who knows, that may be completely useless advice in 2 years. But for now, at least, learn to use programs that are fit for purpose. Now I am going to let you go because unless there's a seminar in 2 hours that I'd forgotten about, you are actually finished this time, and I will see you in 2 weeks. And also, if you're one of the people I haven't met yet, I've tried very hard, but you're more than welcome to come down and say hi and tell me your name. I like to meet everybody. You don't have to, but you can. There are ways, I wouldn't put equations on it, but yeah, like, you know, what's happening inside, yeah, you can think of it that way.
And then I thought about it a bit more. Again, this is just like what occurred in my mind. I hope this is interesting.
It's fine.
But I thought about appearance, because appearance is like a very direct, easy analysis to make.
Yes.
I thought, what other boundary do you think of? And you know, in calculus, it's like such an astonishing thing, like that works up and then with theorem calculus. But then I thought about, like, in real life, we kind of always evaluate the course. Like, for example, even with the exams, we evaluate what the student did throughout the semester with like tests and then yes. So I thought it was cool how it is very cool in what's very cool in calculus is like kind of assumed already.
Very nice. I like the way you're thinking about this.
And then one last question.
Yeah.
So the sentence is like, what's happening in the region is reflected around it. What do you think is lost without? If we were to say also in like a simple sentence, what's lost? What would be, if we could try to simplify that, would it be...
There is a subphysically which is shooting an extra structure. So nothing is so much lost, but you don't know about the structure inside.
Yeah.
You just know totality.
Yeah, so
Yes.
to be, like, for example, a shape of a picture is obviously we're not going to do
Yeah.
inside the body.
Yes, so you lose internal structure. You can only measure broader scale. But this is what science does, right? Experiments don't often see, you know, when you do, when I've done sort of experiments with my biology guys, they tell me about, 700 ants moved this way, and 600 moved this way. They don't tell me about what any one individual. So it's about, think about structure on the scale of the whole. Good question. Enjoy your break, Heidi.
And then you think about projecting that magnetic moment.
I was talking about curl of F dotted with like in Stokes theorem when we're talking about you're saying the curl of F in the direction of the normal. When you say stuff like this, it's like, does it help, or am I supposed to have an understanding, make like visually, I guess, of like what that means or like what I'm actually doing outside of just the mathematics?
So there's a bit of individual preference to the answer to this question. I do like to have a picture, which is why that picture of the hemisphere, where all of the vectors were sort of very clearly running in the tangent space. I couldn't have, so because I know the relationship between tangent spaces and normal vectors, I can say, that means that the projection onto the normal vector is 0. But what I would suggest there is don't think about things like projections necessarily, like eventually think of them as their definition, but think of it as the amount. If I say the projection onto the normal vector, you can think how much of the arrow is pointing perpendicular to the surface. That's about as sophisticated as it is. I wouldn't expect you to be able to construct global conclusions about the curl from that phrase.
Yeah, I think it's also like I have a clear visual understanding of like here's the field, here's what like F looks like, right?
Yeah.
And then if you were to say, take the curl of that and then plot that.
Yeah, it is very hard to connect those two pictures without a lot of time.
Yeah.
I would not expect you to be able to do that. Not one job.
Okay, because that was kind of where I was missing.
No, absolutely not.
Okay.
No, good question. No, I wouldn't expect that.
Okay.
And like in time, you can start to sort of see it. Like I looked at that thing and I was like, okay, so there's some circulation there and some circulation there. But like I know what I'm looking for. I've done this for way too long. No. Connecting specifically curl is a very difficult thing to develop intuition for because it's so tightly connected to other So your understanding really is a 3D understanding. Hard to do. In 2D, maybe I could expect that maybe if you want to develop some intuition in that line, try developing it in 2D. Because in 2D, at least things like the axial rotation and stuff are taken care of for you. And then challenge yourself to see if you can identify what that means. That's not a bad idea. Or don't, or just learn the calculations. Like, that, I don't...
For the sake of them.
No, but not, right? Like, a lot of every day, if you ever talk to an analytic geometer, they are like moving symbols around like it's nobody's business, and they get to the end and they're like, all right, I've done a lot of manipulations, now let's figure out what this actually told me.
Right.
And they won't intuit all the steps in between. The steps in between will be rules, predicates, and theorems, and laws, and then they'll get to the bottom and be like, this has told me something.
Yeah.
Probably need to understand now what that is.
Yeah.
So, there's... What you are saying is not something you need to worry about.
Brilliant. Okay. Are we lunching?
Yeah, we're lunching. Thank you.
Hi, take it easy, guys. See you in a couple of weeks.
Two questions. The first is, do you know if there's a blanket rule against people tutoring if they're not, being tutored if they don't take honors?
Oh, God, there are new rules about this, and it is... I happily have managed to avoid this rule because all of my tutors are PhD students. There's a rule, and I don't know what it is. If you want to tutor, you can submit an EOI. I think you are an undergrad, and it probably won't get up.
Yeah.
But No one's stopping you from asking the school office who to contact.
Okay.
But I think, I don't know, but I think you might be out of luck. However, there is also the Math Help Center, and they, I do believe, take on strong undergraduates who performed well.
Do you know if is this Math Center an official thing RUA does?
It is. It's not run by the School of Math, though. It's run centrally. But we connect with them a lot. It has a name, and I can't remember what it is.
I'll try that.
Yeah, okay, because they, I think, will take on strong undergraduates because they are not formal tutors. It's a different thing that is not run through the academic wing of the university. So it's not subject to the same texts or rules that we are.
Okay, cool. And my second question was, if you're hypothetically marking an assignment, and in this assignment you asked a question that had completely unintended, a totally unintended extreme, proof inside of it that was completely non-trivial. The question is meant to be kind of easy, but there's one assumption that you have to make, and proving that assumption is very difficult. Would you prefer to see it proved, or see it ignored, or see it? And if you saw the proof, would you think the student used AI?
We certainly wouldn't do the last one. We are fully aware that if you did something like this, you're far from the only one. There are lots of students who theorem limit their way through some of the more subtle points. So if this is a concern for you specifically, hypothetically, about this recent assignment, don't worry about it.
No,
My markers are really understanding of what to expect from advanced students, and that some of them will go down these little holes and poke things with sticks.
It's an algebra assignment, and
that I can't promise.
no, the tutor has not considered that 0 is an ideal, and when you take 0 as an ideal, your entire argument falls apart.
I don't think anybody will, no one will penalize you, no one will say you used AI, although technically you're allowed to anyway, so we couldn't penalize you even if we wanted to. But no one would be annoyed, and we are quite used to students clarifying these little corners. Yeah. However, I cannot speak for other academics, so take that as general advice rather than...